Okay, our topic is tangent lines and rates of change, and some of you have seen this before, so what I need to caution you on is that you cannot use the shortcut to the derivative until we have all learned it. So we'll be sticking with the definition of the derivative. So given a secant line of a curve from Q to P, the secant line approaches the tangent line at P. Okay, so what does all this mean? So here in the pink we have our function f of x, okay, and what we want to do is take this line right here that is cutting through the curve, which is our secant line, okay, and what we want to do is identify the slope of the secant line, all right, and compare it to the slope of the tangent line. And in order to do that, we need to decrease the distance between this point Q and this point P. So what we have is the given point for P, A, comma, f of A, meaning this is, my function is P, and, or excuse me, f, and I will plug in A and get f of A. So that will consist of my point P. And then I have the point Q, so what we have is some given value x, okay, and we plug that into our function and get f of x. And what we want to do is decrease the distance between these 2 points, okay, and we would find the slope of the secant line by taking these 2 points and using the slope formula, which would be f of x minus f of a all over x minus a, which is essentially y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So it's the change in y over the change in x. And we use this formula when you have 2 points on the graph, okay, and you are trying to find the slope of the secant line. But what is more accurate is the slope of the tangent line, okay, and this is when we have 1 point, okay, 1 point. So in order to do that, we need to decrease the distance between these 2 points. So basically this point is going to come to point P. So if we decrease the distance, that means x will get closer and closer to A until they overlap each other. We are evaluating the limit. That's the whole reason that in Unit 1 we evaluated the limits. So we're going to evaluate the limit as x approaches A, meaning this value will approach this value, of f of x minus f of a all over x minus a. Okay, and this is the standard formula for us to find the slope of the tangent line. Okay, so sometimes we have 2 points, sometimes we have 1 point, it just depends. But when we're looking to find the slope of the tangent curve, we can use the slope of the secant curve to approximate that value. So here, let's see what happens when we are asked to find the slope of the tangent line to the given curve at x equals 1. So first of all, I have the point, we're just going to do it just like we saw up here, the point 1, f of 1, okay, so that's point P right here, okay, and then point Q is going to be x, f of x, which is what we have up here. Okay, so what we're going to do is use this formula because we only have 1 point. Okay, so we need to find f of 1. So when we evaluate f of 1, that's my y value. 2 times 1 squared is 2 minus 1, just so happens that it's also 1. So to find the slope of the tangent line, this is equal to the limit as x approaches 1 of, here we go, here, f of x minus f of a, which is 1, okay, so it's f of 1 all over x minus my a value is 1. So what we need to do is replace what we know with any type of function here. So we have the limit as x approaches 1 of f of x. So they gave us f of x, it's right here. So this is 2x squared minus 1 minus f of 1, which just so happens to be 1, all over x minus 1. So we want to use direct substitution. Right now we can't. Okay, we'll get a 0. So let's simplify. The limit as x approaches 1 of 2x squared minus 2 over x minus 1. Still cannot use direct substitution, so let's factor out a 2, and this becomes a difference of squares, I think. So this is the limit as x approaches 1 of 2 times x squared minus 1 over x minus 1. If we use direct substitution right now, when x is equal to 1, we end up with 1 squared minus 1, which is 0 over 0. So we can't do that. So we need to do some algebraic work. So we have the limit as x approaches 1. I'm going to factor this difference of squares over here. It was a difference of squares. 2 times x minus 1, x plus 1 over x minus 1. So what that allows me to do now is cancel out this x minus 1 and this x minus 1. So we have the limit as x approaches 1 of 2 times x plus 1. So once I've used one of my techniques, I'm going to try direct substitution when x is equal to 1, and I have 2 times 1 plus 1. So that means we have 4, which is the slope of the tangent line, which is what I wanted. So for those of you that know the shortcut, you could figure that out, but we will get to that later. So there's my slope of the tangent line. Find the slope of the tangent line. Done. So another way that we can express this formula for the slope of the tangent line is to consider the point x, f of x, and then some difference in the x direction, which can be expressed as either h or delta x, meaning the change in x. So now what we have is the tangent line of the formula becoming the following. So if we're changing the distance, if we say that we have the point P right here where we have x and then f of x, okay, and we have some distance here between these two, so let's call the distance h. That means to get from here to here, I would add a distance of h, meaning if this was 1 and I wanted to get to 5, I would add a 4, so this would be 1 plus 4. Well, now this is just very generic. Okay, so now what we have is the point x plus h, and then this would be f of x plus h. Okay, so that would be point Q. So we have point P, which is x, f of x, and then we have point Q, which is x plus h, and then f of x plus h. Okay, and what we want to do is decrease the distance between these 2 points. Okay, so this is the slope of the secant line, and we want the slope of the tangent line. So I drew this in right here. Okay, so we want to find the slope of the tangent line. So we'll use our formula, but what we want is this distance between these 2 points to become 0. So we want the distance from here to here, see this gap right here? We want this point Q to travel all along this curve, so now the distance between these two is 0. So we want the limit as h approaches 0. We want the distance h to be 0, meaning we don't want a distance between these 2 points. Okay, and this is going to be f of x plus h minus f of x over, okay, x plus h minus x, meaning this is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So you notice here my x's go away, and this gives me my standard or my formula for the slope of the tangent line, which is the definition of the derivative. The limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so this is the slope of the tangent line formula. Okay, so this is definitely important. And again, what we want is to shrink the distance between this point and this point until the distance between the two is actually 0. So another way that you could see this, if you were looking at it somewhere else or in another textbook or on a worksheet, is that instead of h, you see delta x, meaning the change in x. I want the change in the x's, or the difference between the two, to become closer to 0. So if you were asked to find the equation of the tangent line, you will need a point and a slope, And you can easily leave it in the point slope equation, which for those of us who have forgotten, it's been so long, y minus y sub 1 is equal to m times x minus x sub 1.